I am going to try to show you how to find the strength of an electric field due to a line of charge some distance away, and we'll look at it at the center of this object. So let's make the point. We're going to make the point that we want to know the field right here, and we'll say that that is a distance A away. Just making stuff up, right? The charge of the small wire, we can say, is going to be Q. It'll be positive. And that has a uniform charge density, which means that the total charge over the total length is the same as any small packet of charge over that small section. So if I look at a little section of that line of charge, there would only be a small portion of that total charge in that location. Now that small packet of charge is going to contribute electric field that would be along a straight line to that point in that direction. And if we take a section that is about the same distance away on this side, that's going to attribute field in a straight line direction pointing that way. Since electric field is a vector, so these are the little components of the total amount of electric field by the entire line of charge. Since they're vectors, the horizontal components of those vectors are going to cancel each other out. So that component and that component. We are only worried about the vertical components here. So the amount pointing down from each of those, and every other packet of charge that is going to contribute electric field just at varying angles. So that one's going to contribute there on the other side. Even the ones right here in the middle are contributing straight down, all the way out to this edge, contributing over here. But it always is symmetric so that the horizontal components always cancel out. Let's take a look at the dimensions between the line of charge and the point that we're looking at. So, well, let's pick an angle, and we'll use the angle here as theta, so that if I take from, that's the line of charge, this is coming down from the center point to the point that we're worried about, and that would be the distance A away. At this point, that's where L over 2 is. And we take any little packet of charge here, and that would be the radial distance from that amount of dq to the point that is a distance A away. The angle we picked up here will go here within that triangle. This is going to be important when we try to solve our integral here. So the electric field is equal to the sum of 1 over 4 pi epsilon naught times the charge that's producing it over the distance squared. and we get a small amount of electric field from every small amount of charge. And we have the distance r as the distance from the charge to the point. If we think about each little packet of charge contributing field at that point that is A away, the r distance, which we're showing down here, changes as we move out to the end of the line of charge. So the r is a variable, so we can't integrate that with a variable in there. Our challenge is to make the proper substitutions in order to have one variable and everything else constant. The first constant we have is the charge density. So we can see up here, if we solve that for dq, we can substitute that into this equation right here. And the dx is related to the distance away from the center point out to the total length. So we're really integrating this between the parameters of the position negative L over 2 to positive L over 2. We now have to get rid of the variable r and put it in terms of the x position, because that's what affects, if we look over here, where this dq is along this axis is going to change the angle, going to change the r. So let's look at that triangle here. We want to get r in terms of the horizontal distance and a, and we can do that using the Pythagorean theorem. So we know that r squared is equal to a squared plus x squared. So our variable is the position x away, and a is a constant now. We also need to get the angle theta in terms of constants. So if we look at this as the cosine of the angle theta, we have the adjacent side, which is a, over the hypotenuse, which is r. We just found what r is from the Pythagorean theorem. So if we substitute r squared in for r squared, and then we have to think about where this cosine of theta is being used. I probably should have got to that a little earlier. We talked about it, and we are only interested in the vertical components. So if I leave my equation as is up here, then I'm getting the value along that line. I only want this value. So if I take the cosine of theta of this value, I'll get only that vertical component. So let me add that to those two equations. And since theta varies, that's where this comes into play. We then end up with a constant as well as that constant and the variable that we want to integrate with, which is dx. So let's make those substitutions. So I have that dE is equal to, and I'm going to pull out the constant lambda over 4 pi epsilon naught times the integral, and I'm going to add my limits in there, going to L over 2 from negative L over 2, and then I have dx over r squared, which is a squared plus x squared, times the cosine of theta, which is equal to a over r, but r is the square root of a squared plus x squared. And we can combine the bottom terms. And do another trick here. Since we have symmetry, and we're going from negative L over 2 to L over 2, what we can do is double the value from 0 to L over 2. So by going half the length, we know that the other side is going to contribute an equal amount due to symmetry. We'll go from 0 to L over 2. And we have a over a squared plus x squared, 3 over 2 dx. That looks fun, doesn't it? So you either have to use your new fancy-dancy calculators or this gem in your textbook in appendix page A11, which is a table of integrals. So if we look at our integral that we have, it matches up with number 19. Some people get this confused with 18. However, in 18 there is a variable x at the top. Ours doesn't. Ours has a constant at the top. So using this table of integrals, we can solve that pretty easily. So we have that the total electric field, let's move that up, which is really what we're doing anyway, the total electric field is equal to, I'm going to pull that A out, we have 2 lambda A over 4 pi epsilon naught, and then this would just be like the integral listed above, so that our solution is going to be x over a squared, because it's the same variable, a squared plus x squared to the 1/2. Now we have to plug in our limits of 0 to L over 2. Moving it all around, let's plug in our values here. So we'll have E equal to the constant, and L over 2 goes on top in for x. Still have a squared times that a squared plus L over 2 squared, which would be L squared over 4, and that's still to the 1/2 on the bottom. We have some simplification we can do, but I'm going to get rid of a lot of this so I can move around on my screen. All right, so this 2 and that 2 can cancel. This A can cancel with one of those A's. So we're left with lambda L over 4 pi epsilon naught times A. I'm just going to write this over to the side. 1 over A squared plus L squared over 4 to the 1/2. That's what the electric field is equal to. Now there's one extra step that we can do. We know that the lambda is equal to the total charge over the total length. So you can make that last substitution. And you can see that the L's will cancel. And you have it in terms of the charge now. Now there is a problem on the WebAssign that uses this. And depending on how the information is given, you may want to use the charge density, or if they give you the total charge of the object, this final form. Now, you should get some practice working this out. It's going to take a while to learn how to do this, but we have to do this in a few future chapters. So the more used to this you get early on, the easier it gets later.